Okay, I'm going to take a look at problem 1466. And this is a girl with a certain mass, 40 kilogram mass, is swinging on a swing set. And it gives you some information here on like the maximum height. So you can figure out the maximum height from this angle that's defined. And as this the swing is moving along its path, what we care about is we want to find out how much force is acting down on. There's actually four posts, so these are two of them that are shown, so it's only shown in 2 dimensions. But we have to make sure we include the other two posts that aren't being shown. Um, we want to find out uh, the force basically at on these two posts when the girl's position has moved basically vertically, right here. Okay. Okay. So what are we looking for? Basically, we're looking for the force at theta equal to 0. Okay. So although I didn't draw it in here, it's basically the vertical when the swing has become vertically here. All right. Now we need to, one of the things we need to do is we need to pick a datum point. So we'll do that. And I'm going to choose it as same as the author did at point A. Okay. First part of this, like any other problem, typically I go through and I'll put in the information that's given. So we have 40 kilograms mass, and we have a height max. Okay, so the swing is going back and forth here. Here's represents a post, and here's another post. And we can figure that very easily by just saying, here's the 60-degree angle right here between this line, which represents the girl swinging. This is 60 degrees. So we just want to find the horizontal, or not, sorry, the vertical component of that. Since the angle's right in here, that's the adjacent side, which is the cosine, okay? So since we defined this as being, point A as being like where our datum point is, um, the distance will be 1 meter down from it then. Okay, so the maximum height out here is actually 1 meter down from A. So I'll just put that in here, right here, saying H max is 1 meter, minus 1 meter down. Okay, then the other piece of information is well, this is the 60 degrees. This is the 60 degrees where the swing is going back and forth. The other piece of information is the 30 degrees for the posts. Okay, so right off the bat, we know, this is a conservation of energy problem. So we'll put the conservation of energy equation in here. So there's some energy associated with this point, the maximum point. And then as the swing goes down, gets down to here, we have some energy at that point too. Okay, so we have potential and kinetic energy associated with this, and except and some potential, or at least potentially, we have some potential and kinetic energy associated with this position. Okay. Okay. The next thing is, in terms of this, this is basically the girl swinging back and forth along a radius, and we want to find, we need to find basically the tension in this cable, right? The swing cable or swing chain. That's going to be the force that's pulling down against the posts, right? So that's the force we need to find, right? That we need to find that force. And that will give us the tension, right? So we need to have an equation that represents a force that's related to the acceleration, right? And it's, in this case, right at this point here, there's mass times acceleration in the normal direction, right? We need to consider that, right? Now, in this case, the normal component is actually pointing straight up, but we'll take a look at that, all right? So in general, we have the equation, um, our motion equation, and we care about the normal component of that, right? So that will give us, we can use this information to actually get the tension in the cable, all right? Now what we're going to have is we'll have some forces acting up in this direction on the post, and then a tension pulling down, okay? So we'll use that. We need to have this equation, the equilibrium equation for the post, to actually determine that. All right? So there's three parts, essentially three parts and three equations. But let's go draw it out. Let me go back. Okay. So first part of this, and this is approach I took, which is a little bit different than the author, but not much. Um, Come up with a free body diagram, the kinetic diagram of the person. Okay. So very, very quickly, what I said is I have tension going up, weight going down, and mass times acceleration going in the vertical direction, positive vertical direction. Okay. So here is the equation of that form. Well, what do we have? Here's my tension. Subtracting the weight equals mass times acceleration in the normal direction. And of course, this is from our kinematic equation for the normal component of acceleration. Just the velocity squared, that point, over, the tangential velocity squared at this point, and over the instantaneous radius of curvature, okay? Well, the radius of curvature is going to be the same for this entire one, right? If we look back, I didn't write that down, but it's 2 meters. The length of the chain here is 2 meters, okay? All right, so we have that equation. The next thing we can look at is now that we could solve for tension, right? Somehow, as long as we know what this velocity is, we can solve for tension. So we don't know what the velocity is yet, right? The next thing we could do is we can look at the free body diagram of the posts, all right? So this is just a summation of right when the angle is 0 degrees, and actually anywhere along this point, but we're taking it right at 0 degrees. All the tension is going to be in the downward direction or in the y direction, okay? And then we can get the vertical components of those 4 posts, all right? Each post represented as 2F. Well, we have 2 of them because we have one on this side and one on this side. We actually have 4, but so the 4 is going to be basically 2 times 2 times F. So F represents a force of 1 post, okay? So this is, we have the 4. And then it's cosine of 60 degrees here. Okay, so this is an error. This should be 30 degrees here, okay? So make that change. On the next page, I actually put it in as 30 degrees. Yeah, just make sure you make a note. This is 30. This should be 30 degrees, okay? As I was going through, I looked at it and started thinking about it. Oh, wait, that's not 60, that's 30. Okay, so here's the other equation. Just make a note of this. Let me see. Okay, I put the correction in here for this one. So it's 30 degrees there. Okay, the next thing we need to do is now, if you look at these equations, the first one is like, okay, I don't know what v squared is here, right? So, and I don't know what tension is. This is given. Well, this is just gravity. This is given. So this is given. This is mine too. So I don't know v, and I don't know t, okay? All right, the next thing when we did the free body diagram of the posts, we have 2 unknowns. We don't know what F is, and we don't know what T is, okay? So what we need to do, of course, is we need to have another equation to find velocity, right? And then we can use the velocity to find our tension in this equation. And then we can apply tension down here to find F, okay? So here's the third step, is basically you're going to apply conservation of energy equation and solve for V2. Okay? Okay, here's conservation of energy equation. Here's like my initial kinetic energy when the swing is at the highest point. At that point, the velocity is 0, so there's no velocity when the girl reaches the highest point on the swing. And here's the potential energy at that point, okay? And I used the -1 because we said point A, essentially, the horizon that intersects with point A is basically our datum point, or it is our datum point in this equation. So here's the weight at that location. So there's the potential energy. And here's the, at point 2, which is when the swing reaches the lowest point, this is the kinetic energy there, which we don't know what V is. And here's the potential energy there, okay? So we just take these, substitute and divide by the 20 from here. Here's the 392, here's the 784. We use that to find our velocity, which is 4.43 meters per second with 3 significant figures, okay? The next thing we'll do is we're going to substitute back into our motion equation, which was what we found found in step 1, or if we set it up in step 1. And it's just the tension minus, this is the weight going down, is equal to mass times acceleration in the, here's my mass times our normal acceleration at that point, okay? So I substitute in for the velocity, and this is just like the intermediate step, and we come up with 784.8 newtons. I made it 3 significant figures and came up with 785 newtons. Okay. Then the last step is substituting back into the static equilibrium equation in step 2, which is just 2 times 2f cosine of 30 degrees minus the tension now that I substituted in equals 0. So now we have final force of F for each one of the posts is 227 newtons. And that's it.